is Science Max, Experiments at Large. Science Max!
Greetings, Science Maximites! My name is Phil and welcome to Science Max Experiments at Large. Today we're going to be looking at air pressure and friction and simple machines like levers, pulleys, and gears. We're going to look at some rotational energy, some spring tension, and gravity. We need all those things because we're building Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg machines! Rube Goldberg. You heard me say Rube Goldberg machine? Okay, we got that part? Okay, good. Rube Goldberg was a cartoonist who came up with the idea of having a simple task done by a machine that was extremely complicated. There are Rube Goldberg competitions all over the world, and there's only a few rules. First, a human can only touch it once by starting the whole thing off, and then the machine has to work all on its own. I know what you're thinking. You're thinking, Phil, what's the science behind a Rube Goldberg machine? Well, it's all about changing energy. Remember, you start the whole thing off with just a little push. But if you want the machine to keep going and going and going, you have to come up with clever ways to add more energy to the system so you've got more energy to keep the machine going. So check this out. A bunch of stacked dominoes, which will start a chain reaction that leads to this mouse trap, which has all of its energy stored in the spring tension, which will release the ball. Boing! Check this one out. It's a bunch of pulleys, and there's a rope that goes up and down and up, attached to this lever where there's a ball, and there's a big, heavy weight here. And when the weight gets knocked off the table, the ball falls into the hole and then goes down the tube, and so on. Check this one out. Here's a great way to change the direction of something. Say the ball falls on this lever. Well, it's weighted on this end, but then the weight falls off, and the ball goes this way. And, the portal turned on. I gotta pick an expert. Okay. Hold on a second. 10 seconds before the portal resets. Sonia from the Ontario Science Center. Perfect. And there we go. Tons of time. 3, 2, 1. Sonia!
Hey.
I portaled in 3 blocks away. I had to run here.
Okay. You're here now?
Yeah, I didn't put the coordinates in when I left. Anyway.
It's okay. Breathe.
Sonia from the Ontario Science Center. I'm glad you're here because we are gonna build a Rube Goldberg machine.
Really?
Yeah.
Oh my gosh, I'm so excited.
Yeah?
Yes.
I'm excited too. Check it out. This giant room. I've never done anything with it, so why don't we build a giant machine in here?
Why not?
Okay, so here's the rules. The Rube Goldberg machine has to start with one simple thing, right?
Yep.
So we're gonna start with this marble, and we send it on its way, and then a whole bunch of stuff happens, and at the end, we press that button.
That button?
Yeah.
What does it do?
I've never used it before, but when we hit that button, we get cake.
Cake?
A cake will portal in and we'll have cake.
Oh my goodness, can we get chocolate cake?
We can totally have chocolate cake.
All right, now I'm really, really excited.
Okay, so can I start?
Absolutely.
Great, because I saw some stuff over here.
Okay.
This is a pendulum. It's a weight that swings. It swings back and forth. Pendulums are pretty simple. It swings back and forth. Predicting the path of a pendulum, pretty simple. It's gonna swing back and forth. But wait, as I make it so much more complex by adding a pendulum. Now I've got a pendulum down here, and that one swings back and forth, and I've got a pendulum up here that swings back and forth. What will happen to this part of the pendulum when I let it go? Can you predict? Let's find out. This is a double pendulum, and predicting the path of a double pendulum is really difficult. It's still simple physics, but because there's a moving part attached to a moving part, it makes it way more complex. So, the question is, can we max it out even more? Of course we can. These are chaos pendulums. This one's a lever, and it's got another lever on the end. Whoa, and this one here is a perfectly balanced lever, and it's got a pendulum on either side. Whoa. Scientists and engineers have always said that the more moving parts something has, the more complex they are. Science. Sonia and I are taking turns building our Rube Goldberg machine. The first section was my turn, and I explained it to Sonia. Right here, we have what is known as a ramp. Ooh, yeah, I know you know.
Fancy.
That. Right, so we put a marble on the ramp that rolls along this thing into what is known as a pylon. And then we've got these guys right here, which are dominoes. And when that falls off the table, it'll pull on the string, and then it's attached to this. Now, this is the release mechanism, so when that string gets pulled, it will let go, and it will fire this, which is a trebuchet.
All right, should we test it out?
Absolutely. You
Can
want
I
to try
try
it?
it?
Please.
Yeah.
Okay.
Okay, 3, 2, 1. Huh.
Wait.
Didn't go. Why didn't?
Well, the domino doesn't seem to be heavy enough to make this contraption fire.
You know what, Phil?
What?
I have an idea.
Oh, yeah?
Maxed out dominoes.
Maxed out dominoes. I love that idea. Why are they maxed out? Do they glow in the dark?
We'll see.
Do they produce electricity?
We'll see.
Do they talk to animals?
We will see.
Do they dissolve in water? Whoa, maxed out dominoes.
That's what I'm talking about.
These are very maxed out. Okay, so
we
now.
started off with this domino. Then we went bigger.
Yeah.
Bigger, 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 bigger. And we went to the biggest.
Right.
And this is where we're gonna get the most weight, which is gonna trigger it and release.
Ha ha! Here we go. 3, 2, 1.
Here we go.
The one thing to remember about Rube Goldberg machines is they never work perfectly every time.
Didn't go.
But we tweaked it and adjusted things, and then.
Here we go.
3, 2, 1. Whoa!
Nice. That was pretty far.
Yeah, check this out. Whoop. Okay, so
Nice.
now that we've got the trebuchet firing, and the ball is going over there, we need to get the ball going over here
Yeah.
to
The
cake button.
cake button.
I can't wait for the cake. So I have an idea. Come on.
Okay.
No, wait. Changing direction stuff is over. on us.
Okay.
Now we're gonna talk about tension. What's tension? One more than 9 shin. Get it? Because tension and 9 that's okay. Because tension is the force that we usually talk about when we think about pulling a rope or a chain or something like that, because you know the old expression, you can't push a rope. But today we are gonna push a rope. I have a rope right here, and I'm going to push it using another force called flexion. I've got some pieces of plastic here, and they bend or flex. And when they do, they want to spring back. But I'm gonna prevent them from springing back by putting them in between these knots. And look, the rope now stays up. And I take another piece, and I stick it on this knot, and then I bend it all the way. This is not terrifying. Really, it's not terrifying at all. Okay, good. And then I take this piece, and I put it here, and I bend it around, and so now we have a rope that's being pushed, and we're defying gravity, and we're making a cool art sculpture. All right, one more here. Ooh, okay, here we go. And flexing. And whoa. Ha-ha! There you go. I've pushed a rope, defied gravity, and made a cool art sculpture. Okay, well, I guess technically I haven't really pushed the rope because we're still pulling from each knot. And I guess I haven't really defied gravity because that one's sitting on the table and all the others are sitting on top of that. But you can't argue that I made a cool art sculpture. Ha-ha! Art! I mean, science. Sonia and I are maxing out a Rube Goldberg machine. The first part worked pretty well, and now we need to change the ball's direction. This is a trebuchet. Trebuchet fires the ball, right?
Yeah.
Right now I want to tell you the story of the ball. First, it goes through this fancy film of tin foil.
Aluminum foil?
Right, aluminum foil, because it's, yeah, you're right, it's made of aluminum. It enters this large receptacle.
A garbage can?
You also could be called a garbage can. It falls into this conular device.
Funnel?
A funnel, yes, you could call it a funnel. And then it enters the change-o-direction-o-matic, which is a lever. There's a weight on that end, then it falls off, then the ball goes this way.
Phil?
Or that way. The one thing you need most of all when making a Rube Goldberg machine is patience. Ball goes in the funnel, knocks that off, changes direction, and then it goes this way.
Okay.
And that's all I got so far.
So, not bad.
Yeah.
But we really want to get closer to that way.
Right, because that's the button that gives us cake.
How about we use some chemical energy for this?
Ooh, chemical energy.
I have an idea for this one. Let me go get it.
Go for it.
This is my idea.
Okay.
Ball's actually gonna roll down the tube.
Oh, yeah, because this is a rat trap, right?
Yeah.
Which is like bigger than a mouse trap.
And then it's gonna hit it. Yeah. Nice.
Ooh, so this flips around.
Exactly.
And what's this?
That is something called an antacid tablet. Some water.
And the antacid and the water react. Oh!
It blew. Do you want to test it out?
Sure, can I?
Okay.
Okay, ball comes through this, goes down there, comes out of this, and on the ramp.
Onto the trap.
Oh.
And
Ah, so then
Nice.
it fires up
Yep.
and hits something else
Yeah.
and something button cake. So we got a lot of different energies, but you know what one we're missing?
What?
Is electrical energy.
yeah, you're actually right.
I've got a great idea. Hold on.
All right. Let's see what he comes up with.
This is a chain of beads, and this is glass. Now, if I was to drop the chain of beads, what will happen? It will fall. Yes, that's right. It'll fall because of gravity. But watch this. This side goes up. Why? Because of gravity. Wait a minute. Why does one side go up because of gravity? Well, it gets a little complicated, but I can explain. But I think I'll have to put the beads back in the glass. Okay, so what's going on? Well, when this part of the chain starts falling out, it gets longer and longer, and it has more mass than this side of the chain. And if it has more mass, then it has more inertia. And when it starts yanking out very hard, this side of the chain gets yanked up out of the glass very quickly. And when it gets yanked up hard, it flies into the air. But then, of course, the direction has to change, so it goes around a curve and then goes back down. Because of the speed that it's going, that curve starts lifting up over the top of the glass. And that's how it works. There's a big difference in energy because this chain falls far. I try it from here, and it doesn't work as well. Why? Because the drop from here to here isn't as big. You want lots of force acting on the falling chain, which means the higher you do it from, the better it works. So maybe we should max it out. Yeah. But wait, we should wait for it to stop. And now let's max it out. This is a really long chain, and this is a really long drop. Let's see what happens. Whoa! Look at that. Whoa, super maxed out! Science! Sonia and I have used potential energy, the lever, and chemical energy. But you know what one we're missing?
What?
Is electrical energy. Electromagnetism. So watch. The chemical rockets, which we've had from before, they'll fire up, they'll hit the underside of this tray. The marbles will fall and flick this switch. See that sledgehammer?
Uh-huh.
This is an electromagnet, and it will attract the metal in the sledgehammer. Watch this, ready?
There.
There. Magnetized, electromagnetism. Now, when the marbles fall, it'll turn the electromagnet off, and the hammer will fall.
Oh, that's pretty cool, actually.
Right?
Can we
So
try
let's try it. Here's something we didn't know. Predicting the flight path of an antacid rocket canister is almost impossible. We had them aim the same way every time. But we stuck with it, and being patient is key, and eventually it worked. The chemical rockets fire, and they hit the tray. All right!
That's pretty cool.
Yeah, so now we just need hammer hit something, and then something, button, cake.
I have an idea.
All right. Cake any minute now. This is a basketball. It bounces. This is a golf ball. It bounces. but it never bounces as high as where I dropped it from. But watch as I put the golf ball on top of the basketball. Whoa! Why does the golf ball bounce higher than where I dropped it from? How is this possible? I only bounced the golf ball from 1 meter high. So what's going on? Well, as the basketball hits the ground, it compresses, storing the potential energy of its bounce, about to give that energy back as it bounces up again. But this energy works as a springboard for the golf ball. And since the golf ball has a lot less mass than the basketball, the upwards kinetic energy of the basketball is given to the golf ball. So, let's max it out. Ball, on a ball, on a ball. 3-ball bounce. Oh, did you see that? Ball, on a ball, on a ball, on a ball. Quadruple ball bounce. Oh, oh. Oh. No, wait. Turns out getting 4 balls to drop straight down on top of each other is pretty difficult. So, we know the mass of the ball is important. Why don't we max it out in a different way? This is a Swiss ball for exercising. It has a lot more mass than a golf ball. So, let's try it out. There you go. The transfer of energy between balls. A great way to lose golf balls. Sonia has added one more step to our Rube Goldberg machine, a stomp rocket. It's a hammer rocket.
Exactly.
I like
so
that.
what's going to happen is the hammer is going to hit our bottle, which
Right.
is going to release all that air that's built up inside of it. It's going to hit that button,
Wait. The rocket hits the button.
and then we get some
Cake!
cake.
Cake! Oh, so this is it. So we're done the Rube Goldberg machine with this last step.
Okay.
Do you want to do it?
I think we should do it.
Ready?
Ready?
3, 2, 1. Let's pause here just before the cake portal's in and recap the science. A marble on top of this ramp has potential energy. As it rolls down, that changes to kinetic energy, which transfers to some stacked dominoes. They fall in a chain reaction, finally causing bigger and bigger dominoes to fall, giving the last domino enough mass to pull a string, attached through some pulleys, to a quick release on a trebuchet. Now, a trebuchet is a first-class lever, with a weight on one side and a sling and a ball on the other. If the weight falls, the sling releases the ball at the right moment and it sails through the air. It's caught in a garbage can and changes directions on a few ramps and another lever as a teeter-totter. Finally, it falls onto a rat trap, which has more energy stored in the tension of the spring. The rat trap smacks another lever, which flips around, turning over some antacid rockets. This allows the antacid to mix with the water and start a chemical reaction that produces carbon dioxide, which eventually builds up enough pressure to fire the container to another lever, which tips, dropping some marbles on a string attached to a switch. That turns off the electricity to our electromagnet. And when an electromagnet doesn't have electricity, it stops being a magnet. So our sledgehammer starts to fall. Now, our sledgehammer is heavy, so it has both mass and speed when it hits this plastic bottle. All that inertia crushes the bottle, reducing its volume. The air gets put under pressure and pushes out through a tube, which takes our stomp rocket with it. The stomp rocket flies through the air and hits our cake button, which then portals in some cake. Guess we really didn't think that through, huh? The cake should have landed on a table or something.
Would have been nice.
There you go, Science Max Experiments at Large, Rube Goldberg machine. Are you sure you don't want some of this cake?
No, let's
But
let's go.
Behold, Science Maximites, I am Filtron 2.0. I have changed myself into a cyborg to give myself super strength. No longer will I suffer the weakness of human muscles. Behold my awesome strength. Tremble in fear at my might. I may have to give myself some upgrades. Yeah, so, okay. Maybe I'll just give myself super strength the old-fashioned way, using the power of science. Today is all about mechanical advantage, like this fulcrum and this lever, transferring a lot of force over a short distance or a little bit of force over a long distance, and vice versa. We are going to be building a trebuchet. A trebuchet. So a trebuchet looks a lot like a catapult, but a catapult uses elastic force to throw something, and a trebuchet uses the good old lever. There's a lot of weight on the short end of the lever, and on the other side of the pivot is the long end, and we've got a sling here with a marble in it, and we put that down here on the ground, and then we let it go, and whoosh, whoosh, it throws the marble. To build your trebuchet, here's what you need. Something to be your lever, like a pencil. Something to be your weight. I used batteries. You'll need to make a frame, and I use craft sticks and cardboard for that. A way for it to pivot, like a straw and a shish kebab skewer. Then you'll want a sling, which is a rope, and something to hold your projectile, like plastic netting. Finally, something to hold it all together, like glue. Get your craft sticks, make some triangles with one craft stick sticking up. Then get your craft sticks and make a base which you will put on with your cardboard like that. Now you'll also probably want to make some extra supports that go off the bottom there like that. Then get your pencil and cut a piece of straw so that you can see right through it, and you can get a shish kebab skewer and you stick it through the straw like that, and that's your pivot point, your fulcrum for your lever. What you want to do is put your weights, I've used some batteries, you can use anything that's heavy, on the short end of the lever. That's important because a lot of weight here translates to a little bit of weight going a lot faster on the other end. So, a lot of weight on the short end, and then on the long end of the pencil where the eraser is, you want to take a toothpick and stick it into the top of the eraser and then cut it off so it's just like that. That creates a little hook that you put the loop of your string net on so that when it gets flipped around, the loop comes off and then throws your projectile that way. And then of course you need something that you want to fire. I like to use marbles, but gumdrops work pretty well because they're nice and soft. And you put it in and you pull it all the way down, all the way so it's actually resting on the cardboard like this, and then you let it go. And it fires. And there you go, a trebuchet. Now, if you want to research how to build one of these yourself, it is called a trebuchet. Haha, trebuchet. Wait, I can make it come up, but I can't make it go away. I don't know why that works like that. Anyway. So we need to max out the trebuchet. Let's see, I need an expert. Oh, Chris. Chris from Logic's Academy has a trebuchet. Maybe we can use that one to figure out how we can max it out. And of course, because it's a trebuchet and it's maxed out, we want to fire something, so I thought we would fire, pumpkins. Let's go. Good luck, little pumpkin. Hey, Chris!
Hey, how's it going?
Chris from Logic's Academy. I had a problem with the pumpkin. It kind of got larger than I expected.
It's okay, I think this one's bigger than what we need anyway.
Chris shows me a scale model trebuchet. One we can use to test a few ideas before building our maxed out version.
Go on
and
here.
you've got little mini pumpkins!
I know, don't get too attached.
The first is the arm length, getting the right ratio. That means how long one side of the lever is compared to the other. When talking about a ratio, you write it like this, 1 to 2. It doesn't matter what the actual measurement is, just that this side of the lever is 1 of that measurement and this side is 2, or 2 times longer than this side. And it turns out a 1 to 2 ratio arm wasn't great. Well, that could be better.
It could be better.
So we tried a 1 to 6 ratio arm. The 1 to 6 arm threw the pumpkin further, but not a lot further.
Better. Definitely better.
Better. Then we tried a 1 to 4. Turns out 1 to 4 is the best arm ratio.
Whoa! That's pretty good.
Chris also had an idea about hanging the weights.
Because as you see here, these go straight down. And going straight down actually makes this spin even faster.
So when we do the big one, we should hang the weights off the end and not attach them to the end.
That's right. And that'll give you some extra distance.
Excellent. Let's fire this last one.
Okay. 3, 2, 1.
Whoa!
Pretty good.
Yeah. Okay, I wonder when we make the big one, do you think we can get it through the goalposts?
Oh, yeah. I think we can do that.
All right, let's try it. All right. This episode is all about giving yourself super strength using mechanical advantage. Well, here's how you can use a rope to give yourself the strength of a superhero. Ha-ha! I am mechanical advantage using a rope man. To gain mechanical advantage using a rope, you need 3 things. First thing, a rope. I mean, obviously, that's a given, right? You know you need a rope. Okay, good. Then you need something to pull and something that will not move. What you do is you tie your rope to the thing that you want to pull. Then you tie the other end of the rope, you guessed it, to the thing that won't move. Now, you pull from the middle like this. And it's very easy to pull the weight. Why? Because of mechanical advantage. You're using a small amount of force over a longer distance. But what if the weight is heavier? Then you lengthen the rope. Now we pull from the middle and it's easier. Why? Yes, mechanical advantage. A small amount of force over an even longer distance makes it easier to pull the weight. Let's max it out. Mechanical advantage using a rope man, away! High above the city, mechanical advantage using a rope man surveys the town looking for someone in trouble. There's someone.
Oh, my minivan broke down and only 10 feet from my parking spot. If only there was someone who could help me.
I'll help you.
Mechanical advantage using a rope, man. I'm saved. Maybe you should try giving yourself some mechanical advantage using the rope. Mechanical advantage using the rope, man.
Yes. Well, I was coming to that. So I have this really long rope, and I tie one end to something that's not going to move, like a tree. Or a steel coil, if you happen to have one. And then I take the other end, and I run all the way back, and I attach this end to the van.
I call her Bessie.
Then I go to the middle of the rope, and I pull on it sideways like this, giving myself a huge amount of mechanical advantage.
Oh, it's working! It's working!
Pulling.
Mechanical advantage using a rope, man! You're doing it!
Ha-ha!
Well, gee willikers, you did it, mechanical advantage using a rope, man. You pulled the whole van.
And that's how you can use a rope to give yourself super strength. I am mechanical advantage using a rope man. Based on what we've learned from our small-scale trebuchet, Chris and I made a maxed-out version.
All right.
This, I think, is
Wow.
as big as we could possibly be expected to build this.
This is huge.
We have the length of our arm, which
Right.
is important.
Yes, and we've got to add weight here, so
Yeah.
we're gonna like loop this in. Whoa!
Oh, I guess that's because I took the weight off.
Yeah.
So, the arm is 4 times longer on this side of the lever
Right.
than on that side of the lever.
Right. So this arm goes 4 times faster than that side,
But
but we're gonna need a lot of weight.
like our small version, we needed to hang weights on the back of our trebuchet. So I got a rope and put some weights on. But because our new version is so maxed out, we need a lot of weight, which I needed to get on a rope and drag it over. Okay. What's there? And I needed to lift it onto the arm. I needed to lift it onto the arm. I lift it. You know, maybe we should do this together. And you take one end. And we lifted it.
That's gonna be a problem, Phil.
I'm kind of glad that happened because there was no way I was going to be able to lift that.
I know, it was way too heavy, and we need something stronger that can still hold the weight and still give us the hinge that we want at the top.
And once the weight's up there, if the rope broke,
That would be bad news.
that'd be big time bad news. Okay, so we need a new solution for getting the weights on the trebuchet that is not...
Not rope. We need something
Not rope.
stronger, and hopefully that still has the hinge on it up here.
Maybe we have some sort of bar system that we could hang.
Yeah, I'm thinking metal.
Yeah, metal, definitely metal.
Definitely metal.
Metal is better than rope
I think so.
for holding a whole bunch of weight. Okay, let's get that done.
Let's do it.
All right, I got some metal over in the shop over here.
Okay.
Come on down to Sal's Science Shop. I am Sal, and this is my science shop. You want levers? I got the best levers around. Little levers, big levers, all drastically reduced. If you can find a lever anywhere else for less, then you gotta tell me, because I didn't know anybody else was selling them. Come on down to Sal's Science Shop, your one-stop shop for science. Hey, you want some levers? Well, boom, have I got levers. What class would you like? What's that? You didn't know that levers have different classes? Well, there are 3 different classes of levers. First class, business class, and coach. No, first class, second class, third class. It's pretty straightforward. And what do we need when we have a lever? We need a load, we need a fulcrum, and we need a lever. Ha-ha! First class lever, the fanciest of levers. You got your load on this end, you got your fulcrum right here underneath, and then you put some effort into this end, and wow, look how easy that is. Ha-ha! First class. What kind of thing works like that? Oh, I don't know. How about this trebuchet you've been spending all this time watching? First class lever right there in front of you. Second class lever. Look, there's a load right here in the middle. The fulcrum's on this end, and you put your effort into this end, and you lift it, and look, it's a second class lever. Huh? How cute is that? But what kind of thing works like that? It's like a wheelbarrow. The fulcrum is the wheel. The load goes in this, I guess this is the barrow, and then I lift with the handles. Huh? Look at that. Ha! Lever! Third class lever. You got your load on this end, you got your fulcrum on this end, but where is the effort? The effort's in the middle, and it pivots while you move it. Huh? Huh? Where you gonna get that kind of crazy contraption? Salad tongs! Salad tongs! Salad tongs. Look, you put the effort in the middle there, it pivots on that end, and you have the load there. And there you go. First class, second class, and third class levers. Whatever your mood, we've got the levers for you. Chris and I had some trouble getting the weights on our maxed out trebuchet.
That's gonna be a problem, Phil.
So we had to come up with a new system. A metal bar that pivots on the bottom of the lever arm. It's got lots of spots for weights, and we could lift the weights one at a time to attach them all. We start out with 255 pounds. How many kilograms is that?
113.3 continued.
Yeah, that's what I got too. All right, that's definitely enough weight, right?
Definitely.
Okay, let's fire a pumpkin!
Let's do it.
This trebuchet works the same as the other models, but because it's so much larger, we really need to haul on the rope. We attach the arm to a quick release, which allows us to hold it in place until we're ready to fire. Oh, here we go.
Okay.
3, 2, 1.
Whoa!
Oh!
Whoa!
We launched a bunch of the same size pumpkins and got a pretty good idea of how far we were throwing them. Oh!
Wow.
Okay, you know what? We should leave this here so that we know how far that last pumpkin went.
And then try to beat it.
And then we try to beat it. We haven't gotten through the goalposts.
It seemed to handle the more weight pretty well. I think we can add even more. What do you think?
I think we should add all of the weight.
Okay.
This is science max. This is not like science minimum.
Let's max it out.
We
maybe.
totally maxed it out. Okay, all the weight.
All
the weight. All the weight.
Max Historica.
Good morrow to you. I am Lord Fillington IV, and welcome to my medieval castle. My father, Lord Fillington III, had his castle besieged by catapults, and he had to share his prized collection of snow globes. Well, I, Lord Fillington IV, have made a few improvements. First was forgetting about snow globes. Those are so last season. I collect limited edition Science Maximals stuffed toys. And I've collected them all, and I'll never share. Hello? That Lord Fillington has been hogging all the limited edition Science Maximals, and he won't even trade. I mean, look, I've got 3 floofers, and all I need is a Fricto. But he won't trade. Surely you can trade. Never. I have all the Frictos, and I'll never trade. That's it. Time to build it. Oh, you're gonna build a catapult and knock my castle walls down? Well, I've learned a thing or two from my father. I, too, have catapults. Release! Fortunately, we've got a new invention of our own, a trebuchet. Oh, fiddlesticks. They have a duck pate. Trebuchet. A what? A Mother's Day? A Hudson's Bay? A Cabernet? I can't hear you. You've got to come closer. Release! The trebuchet was the best thing around right up until the invention of gunpowder. It could throw farther than anything else, even catapults. What you do, you see, is you put something in there, and then you put a big weight up there, right? And this goes down, that flies around and flies over the castle walls, all from far enough away where he can't get me with his catapults. And it works like this. 3, 2, 1. No, didn't that make it? It's too high, it's too high. Ah! All right, I give up. I'll trade. Oh, that's quite nice. I like that. Oh. And that's how trebuchets were used in history. Sort of. Our giant trebuchet launched a pumpkin pretty far.
Very cool.
But now it's time to max it out further by adding even more weight. All the weight, all the weight, all the weight. So we increased the weight to 425 pounds. That's a lot of weight. Okay, are we ready?
I think so. I can't wait to see what this thing does.
I can't wait to see how heavy it is to pull. Turns out pulling that much weight using our rope was really tough, even with the mechanical advantage of our lever. There we go. We found another pumpkin of the same size, but then we started having another problem. 3, 2, 1, go!
Whoa! Look at how high it is!
What? Whoa! Go!
Whoa!
What? Whoa! So, I think we're going a little too high.
Yes.
It was almost straight up. How far the pumpkin goes all comes down to when the rope slips off the pin at the end. If the rope slips off too early, the pumpkin goes up and not very far. Too late and the pumpkin goes straight, which means it'd hit the ground sooner and doesn't go as far. A 45-degree angle is just right. And how do you adjust it? By simply bending the pin. 3, 2, 1.
Whoa! That was great. Great.
That went way farther than 60. We should have had another sign.
I don't even know how far that went.
Yeah, there you go. Science Max, experiments at large, trebuchet. So, one of us has to clean up the pumpkins and the other one has to put the trebuchet away.
Right.
Pumpkins! Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large, and this is a syringe. You might know syringes from when you get a needle at the doctor, but syringes are used all the time in science because they let you measure very precise amounts of fluid. Now check it out. You push the plunger down, and it comes out the top. Or you could pull the plunger in, and it would suck more fluid in this way. But check this out. I've got a syringe attached to a hose here, and this hose is filled with water. And I wondered if the hose was really, really long, how hard would it be to push this plunger down? Of course, I don't know where the end of the hose is because it was really long and I had to string it all the way around, so, here it is. Okay, so let's find out. Push the syringe down and water will come out the other end of the hose. Pretty cool. You see, this is called hydraulics. Hydraulics is a branch of science that deals with fluids like water. But hydraulics are also a mechanism used in a lot of machines. Check this out. This is a syringe with a short hose on it, much shorter this time. And I press down on the plunger of the syringe and water comes out. And I pull in on the syringe and water goes back in. Because the plunger is airtight, it allows me to push or pull the water. But what if I close the system and take another syringe and attach it to the end of the hose like this? Well, then, if I push this plunger in, this syringe fills up with water. And then I pull this plunger out, the syringe empties. So check it out. This plunger raises and lowers based on what I'm doing with this plunger. And you know what that means? We've made a remote control. Huh? Check it out. So, if you take two syringes and you take a hose and you attach them to something you want to remote control, voila, you can build something like this. We have made our very own robotic arm that you can power remotely with hydraulics. Pretty cool, right? If you want to build one of these yourself, here are the materials you need. First, you need two supports and the arm. I used pieces of wood, but you can use wooden spoons, rulers, or pencils. You'll need some craft sticks, elastics, and a paper plate. And of course, two syringes and a hose, which you can get in an art supply store or a hardware store. Here's how you build your own hydraulically powered arm. First, make the base by tracing holes for your supports the width of a craft stick apart. Cut out the holes and use a craft stick and elastic to secure the supports underneath the plate and on top. Then add some elastics and a piece of craft stick in the middle so the supports won't scrunch together. Because we are holding this whole thing together with elastics. Then get your syringe in there and keep it propped up with more elastics. Then get your arm and slot it in between the supports. The arm should be horizontal when the syringe is half full. Elastics to attach the arm and the syringe. Then push down on this end of the plunger and, ha-ha, you have a remote-controlled robotic arm. You can also max it out even more by adding more degrees of movement. You can make the arm rotate side to side. You can even add a little claw attachment at the end and power it all using syringes. Haha, science and hydraulics. So let's max it out. I just need an expert to help me. Let's see. And over that way. Chris from Logix Academy, of course. Logix Academy knows all about building robot stuff. I'm sure Chris can totally help me. Let's go. Come on.
Oh, hey, Phil.
Oh, hey, Chris from Logix Academy. Great to see you.
What took you so long?
How long was I gone?
And what's with the orange lab coat?
Oh, it happened again. It keeps changing the color of my lab coat, but this time, Chris, I prepared for it, and I wore another lab coat. See?
Blue?
No! Well, you know what? This is happening a lot, Chris. So I wore another lab coat under this lab coat. I'm gonna have to wear a lot of lab coats, though, because this is happening all the time. We should talk about hydraulics, right?
Okay, yes,
yeah, because we
yes.
got some cool stuff planned. Okay, so we're just gonna get the table in here. Whoa, okay. This is the hydraulic arm. Check it out.
Oh, very cool, very cool.
If we want to max it out, what can we do? We could make it bigger, we can make it
What if we did it so that the force you put on this side gets multiplied so that this side's even stronger?
Ooh, what do you call that when that happens?
Force multiplier.
A force, I like that. Force multiplier, it sounds like a video game. So we would have a lot more power.
You have a lot more power, which we could do fun stuff.
Yeah, so if we had like lots of power, what would we do? We'd like crush something.
Yeah, let's crush some stuff.
Yeah, we could crush some stuff. Okay, can we start with syringes though?
Yep.
And then we'll work up as we go.
I like it.
So what do we need? Do we need different sizes?
So yeah, I was thinking we need a small...
A delicious plate of cheese and crackers, my favorite snack. But these crackers are pretty salty, so I should probably pour myself a glass of water first, huh? No, my cheese and crackers! Why? Why does this happen? Why does the water stick to the glass? Well, because of science. And the reason why it happens gets a little complicated, but it boils down to this one simple thing. Water likes to stick to things. Huh? Did you see? Did you see how it stuck? No, of course you didn't. You know why? Because it only sticks on a small scale. See those drops of water? That's water sticking to the surface. But it only works when the surface tension of the water is less than the force of gravity, which is why water drops fall when they get bigger. So it sticks to things. That still doesn't explain why you can pour water out of some containers without any drips, and other containers make it nearly impossible. It's all about the angle. Water will flow very easily when there isn't a large change in direction, like around the curved top of this glass. But when there's a big change in direction, like at the mouth of this teapot, the water can't make that turn as easily. This is also why pouring from a full glass is much messier than one that's less full. Pouring out of a full glass, the water only needs to change direction this much to flow down the side. But from a half-full glass, the water would need to change direction this much. So all this happens because water likes to stick to things. So let's do an experiment and coat this glass with hydrophobic spray. Now, hydrophobic coatings repel water. So if it's repelling the water from the outside of the glass, will we still have the same problem? Well, let's find out. Hydrophobic coated glass, non-hydrophobic coated glass, or just regular glass. Water likes to stick to surfaces, but it can't stick to one coated in hydrophobic coating. That's impressive. Should we try something else? Well, that's one way to solve the dribbling glass problem. Except you can't coat your glasses at home with hydrophobic coating because it's not good to eat. The secret is using a container that has a very sharp angle between where you're pouring the water and the underside of the glass, like this jug. And there you go. Now I can enjoy a nice glass of water with my cheese and crackers. Oh, right, wait, hold on, I will remake the crackers into, see, look, see, it's fine. It's fine, I'm not really gonna eat that, I'm just kidding. Chris and I are maxing out our hydraulic crusher.
Yes, before we get to that, I have a little game I want to play.
Okay, great.
Okay, you can pick either the small one...
The big one!
Okay.
So what's the game?
Simple thumb war. I'm gonna press down this side, you press down that side, we'll see who wins.
Okay, ready?
Yeah.
1, 2, 3, go! Oh, wow, that was really tough. Why was that so hard?
Well, Phil, I'm just really strong.
Wait a minute. My turn. Okay, 1, 2, 3, go! Yeah! See, pushing down on this one is way easier. You wouldn't think that the small syringe would be easier. Why is that?
The reason for it is that you have to push this one down a lot farther than you have to push this one down.
Let's see.
See how far this one goes, and this one's barely
This one
moving?
travels much more. This is how we can exchange a little bit of force over a long distance.
That's right.
To a little bit of distance at a lot of force.
That's exactly right.
Just like the lever, it's a mechanical advantage. But in this case, it's hydraulic advantage.
That's right.
Chris and I push down on small syringes, which gives us more force on our larger syringes. Our crusher was ready to go. Ooh, how about an orange? 1, 2, 3. We squeeze down and... Then we tried a walnut. Are you allergic to nuts?
I am not.
1, 2, 3. When we tried a golf ball, we reached the limit of what our plastic syringes and our hands could do. We need to come up with a stronger, more awesome crushing machine using hydraulics.
That's right. I have some ideas.
Okay, good. We can use metal.
We can use metal.
And we can
go bigger as well.
Ew, this water is gross, but I'm gonna drink this water. Why? Well, because of science. No, but I'm not gonna drink the water like this. First, I'm gonna use the power of science to help me clean it. How? By using gravel. Gravel, yes, gravel. So, say I've got some dirty water, and there are particles floating in that water. Large particles, your rocks, your wood. These styrofoam bits will act as the large particles. You pour it into the gravel, and the large particles get filtered out. See? Nothing but clean, clean water. Yeah, I know what you're thinking, Phil, that's not really clean yet. That's because we haven't done step 2, sand. Sand? Yes, sand. Let's say that these plastic beads are small particles. That filters out the tinier stuff. There, huh? Clean, right? No, it's not very clean. So, we filter the water in the next step with charcoal. What? Charcoal? Yes, charcoal. Charcoal works just like gravel and sand, except on a microscopic scale. Say these bits are tiny particles you can't even see. The charcoal catches these like the sand and gravel caught the larger particles. This is called a gravel, sand, and charcoal filter. The gravel catches the big particles, the sand the smaller ones, and the charcoal the microscopic ones. These kinds of filters are used all over the world to clean drinking water. Ah. Delicious. Science.
Max Historica.
This is Archimedes.
What? Who said that?
It's me, the narrator. We're doing a segment.
Oh, well, I was working. Don't sneak up on a guy like that.
This is Archimedes, an ancient inventor and one of the greatest scientific minds ever. One of his famous inventions was the Archimedes screw, which was used to make holes in wood.
No, that's not what it's for. It's for water.
Right, used to make holes in water.
What? No! Look, did you even do your homework?
Hold on, it's here somewhere.
Look, I'll just show you. You see, in ancient times, we had many uses for something that could lift water up. From a well, or to take lake water from the lake and put it into a farmer's field, and that sort of thing.
Okay, I've got it from here. So, Archimedes invented a screw, and he drilled a hole in the side of that container.
No. Look, just sit down. I'll explain it, okay?
I am sitting. I'm in a voiceover booth.
Good for you. Now be quiet. Now look. What you do is you put the screw in the water like this, and then you want to raise the water higher, you see? And so turn it around like so, and the water fills each gap in the screw, and it starts to come up. It gets to the top, and look at this. Look, we've got water coming at the top there. The water is being pumped up. It is the first water pump.
I see. Still seems like a lot of work to fill a glass, but it's very cute.
No, we made them bigger. We obviously were not going to make them this big. This is not very useful.
Right. Archimedes, one of the greatest scientific minds ever. Chris and I are maxing out a hydraulic crushing machine. We tried one out of plastic, but now it's time to make one out of metal. These are called hydraulic cylinders, and they work the same as our syringes. Small ones on this side with a lot of travel, and then a larger one on this side to multiply the force. And some mechanical advantage with a lever to help us push even harder. We tried crushing a watermelon, and it worked great.
So what else do you want to crush?
We crushed a coconut.
It's cracking. Oh, there we go. Oh, it's gonna leak.
And then a can of pop. Science Max Cola, now in the new, smaller can.
Let's really challenge this press. Perfect.
A piece of wood. We tried to crush the wood, but we weren't able to get it to budge. So it's time to max it out even more.
I think we're gonna need like a multi-story industrial-sized hydraulic press.
You know where we can get one of those?
I do.
Awesome. This is water. Things float on water, like pool noodles and wood and toy boats. And now we're gonna do an experiment with how paint floats on water. How's this supposed to work again? Oh! I'm supposed to take the paint out of the can first. This is a fun experiment you can do at home. All you need is a container, some water, and paint. But not just any paint, special paint you use for hydro dipping. That's hydro, meaning water, and dipping, meaning dipping. Carefully pour the paint on the water and add a few different colors. Then take a stick to swirl it up into a pattern. Then you get something you want to paint, and you carefully put it in like so. But don't pull it out as soon as you get it in. You have to spread the paint away because it'll stick when you bring it back out. And then when you pull it out, whoa! Hydro dip. Let that dry, and then you have a very cool painted toy. Let's do some other stuff. This is a bike helmet. If you put tape on what you're painting, you can remove it later to make parts that aren't painted. Skateboard. Whoa! Oh, that's pretty cool. Now to max it out. Hydro dip pants. Wearing the pants when you do this is super messy and not something you should try at home. But the results weren't bad. Science pants! Science pants! Science pants. One of the ways you can experience the power of water is watching it wash away dirt. You can experiment with this yourself by making your own erosion table. To make your own, fill a plastic tub with sand and tilt it up. Cut a hole in the tub at the low end and put a hose with a trickle of water at the high end. Then to complete your model, fill it with a little happy town. This small model shows how rivers cut their course to the ocean by following the lowest point. Try to design your town and the layout of the ground so the river goes around the buildings.
I'll see you later. I'm gonna take a swim in the river now.
There are lots of ways to experiment. Change the amount of water, or the steepness of the angle. Look at the soil, it's all getting eroded over here. Or the way the town is laid out. Every time you do it, the river goes in a different direction. And have fun.
Oh, phew, I'm tired. I'm just gonna lie down.
And that is the power of water. Chris and I are maxing out a hydraulic crushing machine. What about this? Is this what we're gonna use? We went to the Natural Resource Canada's CanMet Materials Laboratory, which is a federal research lab. Oh, this is good. Oh, look at that! Oh, is this what we're using?
No.
Oh, I can use this. Hold on, let me figure this out.
Maybe later.
Really?
It's just over here.
CMAT is the largest research center in Canada dedicated to metals and materials research.
This is it. This is it.
Right! Hydraulic press. How much force does this apply?
This can do 2 million pounds,
That's over 900,000 kilograms.
which is about 20 cars.
Let's crush some stuff! Oh, crushing! We gotta get the stuff. Okay. We started out with the piece of wood which defeated our last press. And go!
That sound.
Reversing! It turned our wood into a pancake. Whoa, totally flattened! So it was time to try some other stuff. We crushed a ball of plasticine.
That is neat. You sort of made a rainbow.
Yeah.
Aluminum foil.
Aluminum foil.
Yes, it is now a solid plate of aluminum.
And a basketball. Basketball! Good thing we got these earplugs in because when it pops, it'll be loud.
What?
Never mind. This hydraulic press was so maxed out, we had to think of the toughest stuff to crush. We crushed hockey pucks, a safe, we crushed a hydraulic jack with the hydraulic press. This is a metal vise. Hard, strong,
Yeah, steel.
heavy, steel.
Whoa, look at it bend. Wow.
Now it's time to crush a bowling ball. It totally exploded. Science Max, experiments at large, hydraulics. Whoa, nicely done.
So fun.
I should reverse it and we should start cleaning all that stuff up,
Yeah,
huh?
I think so.
Okay, reverse. Greetings, Science Maximites. My name is Phil and this is Science Max Experiments at Large. Whoa, oh, I better spin the other way. Today, we're gonna be taking a closer look at spinning. Well, all things spinning. Spinning, rolling, rotation in all its forms. And when things spin, they're subject to a whole bunch of different forces. And some are strong enough to even counteract gravity. So let's get spinning. Oh. Okay, let's get spinning. We are going to make a gyroscopic whirligig, and it spins, and I don't, which is a good thing. Watch this. You pull the string, and it spins, and it stands on its end. Why does it stand on its end when it spins? Because of angular momentum, which we'll get to later. And here's how you can make one of your own. You will need some craft sticks, string, a small zip tie, a shish kebab skewer, spacers like these wood blocks, and finally some round discs, which you can cut out of plastic or find from parts of broken toys. Now, if you want to research this yourself, look up gyroscopic whirligig. Get 2 craft sticks and glue them to your wooden blocks just like this, and then do it again. Space them apart and glue them to crosswise craft sticks, and this will be your launcher. You put your hand in the small end, and the longer end here is where you put your gyroscopic whirligig. Now let's make that. What you want to do is you want to take a shish kebab skewer or whatever fits the diameter hole of the round things that you're using. I like to use little plastic discs from, these are from remote control mechanisms, but you can use anything you want. I found that this launcher works best with 4 discs of the same size. Just like that. Space them out evenly, glue them down, and cut the skewer even on both sides. Then add your zip tie. Put it right in the middle, tighten it up, and cut off the dangling end. This zip tie just gives you somewhere for the string to hold on when you wind it up. Now for your pull handle. Glue 2 craft sticks and 2 wooden blocks, then 2 more craft sticks on the sides. Then tie a string to the middle, wrap that string around the middle of the whirligig, and aha! You have a gyroscopic whirligig, a pull handle, a rope, and your launcher. Now remember, you put your hand in like this, and you fit your gyroscopic whirligig in just like that, and you pull towards you, and it spins. Oh, and that's what we're gonna be doing today, Science Maximites. We're gonna max out a spinning rig, something like this. It's gonna spin bigger, faster, more weight. It's gonna be totally maxed out. So come on. But first I need an expert to help me out. So let's see here. Wait a minute. Aha! Perfect. Come on, this is gonna be great. Okay, this is it. Hey, Sailita from the Ontario Science Center. I'm really glad you're here. You're gonna help me max out the gyroscopic whirligig.
The what?
Oh, the gyroscopic whirligig. Here, I'll show you. It's this, and it spins, and what works on...
Phil, where are your shoes?
I think these are my shoes. They must have changed into flippers in the portal. Weird.
Want to change them?
Yeah, I'll be fine. Anyway, like I was saying, the gyroscopic whirligig is really good. Let's do it here so that I don't have to walk as far.
Can I see it?
Yeah, here it is. Ready? You spin it up, and it spins, and it goes for a while, right?
Because you made it out of 4 discs, it probably spins better because there's more mass.
Oh yeah, because you know what? I actually have an old one. Yeah, I got an old one here with 1 disc, and it does not spin as long as the 4-disc one.
Could we test the 1-disc one out and compare it to the 4-disc one?
You bet, because you know what that is?
Science.
Yeah, that's science. Okay, let's try it. Ready? Whoa.
Huh, look at that. The 4-disc one spins better longer than the 1-disc one because the 4-disc one has more
mass, therefore more inertia. So when we max it out, we should get something with a lot of mass.
Yeah, more mass.
Wait, I have something. Right. Well, Can you give me a hand?
Careful, Phil. I don't want you to fall.
Yeah, well, I don't want to fall either. It's hard to walk in these.
I can imagine. That's why I asked you if you wanted to change your
Nah, we're
shoes.
fine. I'm fine. Okay, check it out. This is what I was going to. Okay, this is what we can make it into our maxed out spinning gyroscopic.
I don't think so.
Why not?
It's just, look at how big the hole is.
Oh, yeah, because we're going to need something to be the axis, huh?
Yeah, we need like a tree to fill that. I don't
Yeah,
think
you're
that's
right.
gonna work.
Too big. Is there anything else wrong with it?
It's also kind of light. It's not that heavy.
More mass, better.
More mass.
Okay, tell you what. Oh, I know. Hold on. I know. Whoa.
Oh, that looks perfect.
Yeah, and then we got this pole.
To go through the center?
We'll go through the center like that.
Awesome.
And then we'll just weld it together, and there you go.
This will be great.
Yeah, high five.
Phil.
Okay, no, wait, sorry, yeah, you got the thing.
High five.
Well, now I got the thing.
Yeah.
All right, I'll get new shoes, and we'll work on our high
Okay.
five. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that, and then let them go. They fly up and out. The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath. And that is called the...
It's coming.
Oh, come on.
Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No. Max it out. Check it out. Magnus Flyer 2.0 stand elastic slingshot. Wrap it around. Remember, for the Magnus effect to work, your cups need to be spinning this way. The front side rotating up. Oh, and there you have it, the Magnus effect.
I, Magnus, am now taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
Silita and I are maxing out our spinning top. Based on our small version, we decided to make one with as much mass as possible. So we got a 20-kilogram weight and welded it to a metal shaft. Will this work the same way? Well, let's look at the science. Why does a top spin? Well, let's start with Newton's first law, which is an object at rest tends to stay at rest, an object in motion tends to stay in motion. But the in motion has another part. That object also wants to go in a straight line. If you think of a bowling ball rolling along, it would need another force to act upon it to make it change direction. We say that a moving object has momentum. Now, a top doesn't go in a straight line, it spins around, but it still has momentum. It's an object in motion, and even though it's spinning, it still does want to go in a straight line. It's just that that straight line is here. We call this angular momentum. To make a top move this way, or that way, would take an outside force, so it stays upright as long as it has enough momentum. But when it slows down, there's less momentum and it becomes harder to resist external forces, like gravity, which will eventually want to make it topple. Our top has a lot of mass, which means it'll have a lot of angular momentum when it gets spinning. It's just a matter of getting it spinning fast enough. So should we spin it?
Yeah, let's spin. Let's see if we can get it to work. Hey, okay.
Spin.
Oh, we're gonna let go. In 3.
Wait. I can't get it.
What?
Wait.
Okay.
Okay, not fast enough.
We need something to help us get it spinning faster. Maybe a rope?
A rope, yeah.
Wrap a rope
That
around
was
it, like
my
the-
idea too, a rope, because the small one uses a rope.
Yes.
Okay.
Okay, I'll go grab a rope.
So, wrapping the rope up.
I'll let you wrap the rope
Okay.
up. I'll get my holder back on top.
Spin it counterclockwise. We attach the rope and wind it up. You wanna make it super clean. This is some of the best coiled rope I've ever seen. I'm gonna pull the rope. You're gonna hold on to it, but I can't pull really hard because you won't be able to hold it up. Because we don't have to pull hard, we just have to get it going fast.
Yes.
Silita keeps her hand on the block at the top and I pull.
Ready?
Wait a minute, we'll get all the way. Oh. Whoa!
Spinning a lot better than I thought it would. It's still spinning, but it's wobbling.
Oh, careful.
Oh, there it goes.
It works, but just barely.
It might spin better, it might spin straighter.
Yeah.
If we had it spinning, something help us spin it faster.
Yes, faster with more power.
With more power.
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are two motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right. Where was I?
I believe you were at, the reason why this works is...
Right. Pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string. Science. Silita and I need to get our maxed out top spinning faster. We tried a rope, but now we're trying a drill. We get a wheel on our drill and use it on the outside of the weight to get it spinning up.
A little faster.
Oh, it's wobbling now.
A little more.
Push me.
And release.
It's kind of cool that it wobbles that much and it doesn't hit the ground. It worked better, but there's always a way to max it out even more. You know what we need, Silita?
What do we need, Phil?
A maxed out drill. Put it right on the top here and get it spinning very, very fast. Super maxed out gyroscope
Okay.
whirly gig.
Gig.
Is it just the top now?
I don't know. Do you
We
want to
could
be
call it
calling
a gyroscope.
gyroscopic
Well,
whirly
it's sort of a toppy, kind of gyroscopy. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope, nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't want to know.
I don't know if I remember to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air. How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle. So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor.
Yeah!
What was that?
It's my science confetti high five I just made.
You know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor? Silita and I have maxed out our spinning top. The trick is getting something that heavy to spin really fast. We've tried a rope and a drill, but now we have a maxed out drill.
So more power and more speed, which is perfect for spinning this massive top.
Yes, and perfect for maxing out anything. We get it spinning and it works great. The top spins for a really long time. In fact, its mass was so large, it started drilling a hole in the concrete floor. We tried it again, but started to notice something.
The drill is smoking quite significantly.
Our drill began to overheat. Why? Good old Newton's first law. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more mass we have in motion, the longer it will stay in motion. This will go forever. Well, not forever,
Well, not
but
forever.
it'll go a really long time because it's got a lot of weight. But that same mass wants to stay at rest when it's not moving. We have to overcome all that mass wanting to stay at rest to get the top spinning. And even for our maxed out drill, that was a tough job. But once it was spinning, there was only one thing to do. Max it out even more! Silita and I come up with a plan to max out the top by riding it. You want to ride the top?
Of course I want to ride the top.
We can both ride the top. One person's gonna have to drill this, so we'll have to take turns.
Max Historica.
This is Leonardo da Vinci, one of the greatest scientific minds the world has ever seen. And this is a wheel. Da Vinci thought to himself, wouldn't it be great to design a wheel that kept spinning forever? So he got to work. Something that keeps spinning forever without stopping is called a perpetual motion machine. And it was an obsession of Da Vinci's. Why, this is great. The bottles tip the water to the outside, making one side of the wheel heavier, which will keep it spinning forever. Except it doesn't work. You see, what Da Vinci doesn't know is that science says a perpetual motion machine is impossible. But of course it wasn't for another 350 years till scientists figured that out. So we can't tell Da Vinci. What? Oh, never mind. Leonardo da Vinci, one of the greatest inventors ever. Even if not all of his inventions worked. Silita and I got our maxed out spinning top to work pretty well. The only thing left to do was to ride it. We attached a large disc and a Lazy Susan. That's a platform that spins around on ball bearings.
Lazy Susan on top,
Lazy Susan?
so that you can ride on it.
Yes, and then we wanted to add this extra bit. Now, why did we want to add this?
We need a little bit more weight on our top.
Okay, so who gets to ride it?
I feel like you should ride it.
I think you might be right.
Because I want to use
Oh,
the drill.
the super awesome maxed out drill. Okay, so let's do it. First thing I should say is do not try this at home. We are trained scientists. Silita uses the drill to get it spinning while I hold it steady. Then I hold on to our safety line above and carefully rest my weight on the top. It works, but not for long. We take turns trying it out, but it seems we have another part of science working against us. Good old friction. Friction with the air and with the ground is what eventually slows a spinning top down. But our weight on the ball bearings of the Lazy Susan really increases the friction. More friction means the top slows down a lot faster. Whoa!
That was pretty cool.
It was kind of terrifying, right?
Yeah.
Good old Newton's first law kept the top spinning, angular momentum kept it from falling over, and friction slowed it back down.
the forces were always the same, no matter if it was a little top, a maxed out top, or a rideable one.
Yeah! Whoa. There you go, Science Max. Experiments at large, giant spinning top. That's as large a spinning top as I think you.
I think in the entire world.
Let's do it again. Yeah! Greetings, Science Maximites. Get your hard hats out because today we're gonna be building things. Like I always say, what's the point of science if you can't use it to build cool stuff? And today's episode is called Stable Structures. Now, stables are the buildings where horses sleep. So, stable structures means... I think I have the wrong kind of stable. Today, we are going to be building a gumdrop dome. And gumdrops are already kind of dome-shaped, but they don't hold a lot of weight. Yeah, can't hold much weight. But you can make it hold a lot of weight if you build a geodesic dome. A geodesic dome means a round shape made out of straight lines, and that's what I've made here. All I used is gumdrops and toothpicks. It's very easy to make, and I'll show you how to do it. First, you need to start with a pentagon, a 5-sided figure. 1, 2, 3, 4, 5. And then stick them all together, obviously, with toothpicks. Then what you want to do is you want to start making triangles. So you stick a toothpick in here and a toothpick in here, and then you put a gumdrop at the top of this triangle, just like this. And then you make another triangle here, and here, and here, and it becomes a whole bunch of triangles, you see? Easy to make as long as you start with a pentagon on the bottom. Now, once you've built one, I suggest you build 2 more, because then you will have a stable base and you can see just how much weight these hold. Yeah. You wanna max it out? Okay. Let's max it out. Oh, a little collapsing, but still not bad for gumdrops, right? So there you go, the geodesic dome. That's what you research if you want to learn how to build one of these for yourself. But now, let's max this out even more. Okay, now I just need an expert to help me out. Do you like my new interface? It's good, right? Watch this. Oh, wait a minute. That's not, okay. Wait, no, that's not the right gesture for that. It's all gesture-based, so I gotta, this? Nope. This? Nope. That? Ooh, okay. Expert. I want experts. Oh, okay. It's voice activated. Great. Sarah from Mad Science. She'd be perfect for this. Good. Close. I could leave it running. Sarah?
Hey, Phil. Back here.
Hey, Sarah. Sarah from Mad Science. Great to see you.
Thank you. Great to be here. I like your lab coat. It's a really nice color.
Wait a minute. It's supposed to be yellow. It must have changed to orange in the portal. That's okay because this is not the first time that's happened, so I've installed a little secret thing on the app that allowed me to get a new one from storage.
Oh,
Watch
perfect.
this. Huh. Didn't work. Oh well, I'll get another one later. All right. Anyway, we are going to max out the geodesic dome.
Amazing. That's so cool.
Yeah, so we just want to make it bigger. So how do we do that?
Okay, well, there's a couple ways we could do that. We could add a few more points of connection, change the shape of it, make it a little more complex so it's a little bit bigger. Or we can use the design right now and use different materials to make it bigger.
Okay. Well, you know what? I think we should do both of those things.
Okay.
I think we should make it more complex and bigger, but why don't we start with bigger?
Okay.
But we'll use the simple design right here, and we'll just get like long wooden poles instead of toothpicks.
Perfect, yeah. And then, what will we use for the gumdrop?
I guess we can't get big gumdrops, huh?
No, I don't think so.
What about oranges? Huh?
Yeah, oranges could work.
Maybe, yeah, because you could stick the poles in and then the oranges would be, okay.
Yeah, that's
We'll go to the Science Max Fruit Market and we'll get some oranges.
Perfect.
And I'll get a yellow lab coat. I don't know why that didn't work. Is this a maxed out number of oranges?
I think so.
Or is it just a mediumed out number? We don't really need many more oranges than this.
No.
So, there we go. So we got our oranges. Those are going to be our gumdrops, and
These wooden dowels will be our toothpicks.
We just have to start with a pentagon, right?
Yes.
5 sides. So why don't we just lay that out and see what it looks like here?
We start building this dome the same as the gumdrop dome.
So, like this.
We stick the dowels into the oranges to make our 5-sided pentagon.
Good, like that.
And then we go up from there by making a few triangles and sticking the oranges on the tops.
Oh.
But because the oranges are heavy, the triangles are pretty wobbly. That is, until we get them all connected with cross pieces.
Yeah.
After that, it seems to hold up pretty well.
Okay, let's see if it holds it up. Whoa! That's exciting. That is very exciting. Let's do the same thing. So you make a triangle here, I'll make a triangle there, and then we'll connect them.
Sounds good.
2 layers, orange dome. I'm pretty excited about this. This is nice.
Yeah.
I'm surprised that the oranges actually hold it together because oranges aren't really that strong.
No, exactly. But the structure itself is really strong based on the design of it.
Yeah, because it's all about the shapes, right?
Exactly. And we're using lots of triangles today, which are one of the strongest shapes on Earth.
Ooh, strong. Well, then making something out of a lot of triangles makes it really strong.
Exactly.
Yeah, okay, so let's make that top layer of
Right.
things. We only need 1 more orange.
Yeah.
This will be the one, top layer.
Right in the middle.
1 orange on top with 5 dowels from each point and...
Yeah! Orange juice high five.
In fact, it worked so well, there's only one thing left to do.
Is there a way that we can maybe max it out even more?
Watermelon? Watermelon. We could get the round watermelons. Do you ever seen those? They're like the size of a bowling ball or smaller, a little bit smaller.
That's perfect. And they're nice and full inside, so they should be able to hold the posts into place.
Okay, we'll try it one more time with watermelon. Inside dome high five. Yeah! You may have heard of cup stacking, and if not, you're missing out because not only is it fun, but it's something that kids are the world record holders at. And it's all about, you guessed it, stacking cups. Now, I have learned the pattern, but I'm not super fast at it. The world record is actually 4 seconds, and this is what that looks like. But you can't use camera tricks to help you. You have to practice to get faster. Now, you don't need to use official sport stacking cups, but if you don't know your science, some things will work against you. First of all, these cups have holes in the bottom, which makes them not very good as, cups. Why do they have holes in the bottom? Because of science. You see, when you pull the cups apart, there is air that needs to get inside this cup. If you don't have a hole, like these ones, the air makes them stick together because there's nowhere for the air to get in except for underneath, and they will stick. Once again, let's compare. Also, you want the cups to have some weight because if they have some weight, they'll fall out of each other easily. If they don't have any weight, like, say, these styrofoam cups, it becomes very difficult. And cup stacking with trash cans. Okay, here we go.
Even though these trash cans were heavy, they didn't have holes in the bottom, which means they stuck together. A lot. So why didn't I drill holes in the bottom of these trash cans?
Okay, and then...
Well, I needed them in episode 6 to make 11 barrels of slime.
Okay. 2. No.
But I eventually did it.
And time. Okay, there you go. The world record in trash can stacking. I know it doesn't seem very fast, but first of all, that was hard. And second of all, I am the only one to do it. So therefore, I hold the record.
Sarah and I have already made a great dome out of oranges. Now we're maxing it out even more, but this time using
Watermelon!
Watermelons! But not the giant watermelons,
Nope.
the perfect spherical watermelons. They'll have to do pretty good to be better than the oranges.
Definitely.
All right, so we just do it the same way?
Same way.
All right.
Let's do it.
I'm sure I'm not telling you something you don't know when I say watermelons aren't great for building structures
It's
with.
super wobbly.
But the fact that we can make a structure using watermelons just proves how amazingly strong a geodesic dome really is.
Have we done it?
Yeah.
We've done it! Yeah, watermelon dome!
All right, we've got our gumdrop dome,
We've got our orange dome!
and we've got our
Watermelon dome! These are awesome maxed out domes. What do we want to do to max it out even further?
I think the watermelons were a little too heavy. Maybe we should go back to something lighter.
So we can make it out of gumdrops, which will be like more complex.
Exactly.
And we won't get orange juice raining on our heads all day,
Yep.
which is what happens with this one.
Max Historica. This is Leonardo da Vinci.
Ciao.
One of the greatest inventors to ever live. And this is a pile of wood. One of the greatest piles of wood to ever be piled. Now, Leonardo is going to construct a bridge out of this wood. This is Leonardo's hammer. One of the worst hammers in the history of hammers. Now Leonardo must construct his bridge using no tools at all. No, that hasn't been invented yet. How will Leonardo construct a bridge using no tools at all? Well, he is one of the greatest scientific minds. One of the greatest scientific minds in history. Oh-ho! Each piece of wood is supported by another. And that's what's known as Leonardo da Vinci's self-supporting bridge. Leonardo's done it! But there is a flaw in the bridge. It's very strong when you apply downward force, but not so strong when you push on it sideways. Fortunately, Leonardo can devote his great mind to figuring out how to clean up his workshop. Haha! Join me, one of the greatest narrators in the history of narration, next time on more Max Historica. Let's recap. Sarah and I have maxed out our simple geodesic dome, but now it's time to make it even more maxed out. We need to increase how complex our structure is.
So right over here, we actually have a dome that's just made out of triangles.
Ooh, look it. It's nothing but there's a triangle there, there's a triangle there, triangle there, triangle. So all triangles.
All triangles. And see how much bigger it is even compared to our first one?
Yeah.
And that's just by adding more points. Over here, we have one that uses pentagons and triangles.
Ooh, let me see. Okay, so we got, oh, there's a pentagon there.
Yep.
There's a pentagon there. And then we got triangles here.
Yep.
Can we go bigger than this? Because this is good, but this is not maxed out enough.
Sarah had the idea of lengthening the poles
Shish kebab skewers, I love those. I use those all the time in my science experiments.
and making a bunch of pieces that fit together.
So we just make a whole bunch more of these.
Yep.
And then we'll make some sort of big dome.
This is awesome! So we maxed it out, and it worked great. But gumdrops started to become a little hard to work with.
Every time I do one attachment, another one comes apart. So I had to get inside to hold it up with my head.
I think I've got an idea.
Oh, yeah?
Be right back. Yeah.
Okay, but should I get out or should I? It's okay, I can stay in. I can just keep fixing while it's collapsing a bit, but it's okay. Wait, this is inside. No, this is outside. Wait, hold on. Help, Sarah?
Hey, oh, my.
It kind of collapsed a little bit. Gumdrops, they just don't have the strength.
Exactly. I was thinking we could use something a little more sturdy, maybe like some cardboard.
Oh, yeah, and it doesn't move at all. We can totally make this, we'll max this out. I'll just put this over here. Okay,
All
fair
right.
enough. Okay. If you want to build a block tower, you might think the fastest way to do it is just by building a single stack of blocks. But science may have a few things to say about that, and those things would be no. Let's try it with books.
The books are much wider than the blocks, so that will give me a wider base, right? But it's all about the center of mass. You compare how wide it is to how tall it is.
Right now, it's pretty wide and it's not that tall, so the center of mass might be around here.
But if you go high enough, how high it is compared to how wide it is changes a lot. It's getting higher, but not any wider.
The center of mass is probably right around there somewhere, which means it's gonna be really hard to balance that. Whoa, careful, almost. I can do a little bit more, I bet. Oh, careful, careful. Whoa. It'll only get so tall. So there you go. You can never stack a single stack of anything very high. But just in case you don't believe me, let's max it out. Ah, ha, ha. Oh, careful. Now it's time to see how high, how high I can make a single stack of boxes. Okay, and whoa, 6 boxes! 6 boxes! 6 boxes! Whoa! Can he go as high as 12? Let us find out if I can go as high. Apparently not. Can he go as high as 11? Can he go as high as 11 boxes? Let's find out. Oh, careful, careful, careful. And ha-ha! A single stack of boxes! Huh. Okay, well, like I said, you can't stack a single stack of things too high, because it will fall. Ha-ha. Science! 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 This is a pencil. You probably have one of these at home and use it for all kinds of interesting things like writing and drawing, and that may be it. But if you have a lot of pencils, you can build stuff. I'll show you some of my favorite pencil builds. Check this out. It's a pencil cube.
If you want to try building one yourself, you build it like this. Get a piece of foam and then lay out 11 pencils this way, and then another 11 that way, so they make a nice square. Then take sharpened pencils and stick them into the foam in all the gaps. Go all the way around, and then keep adding more layers of pencils, and eventually you will have a cube. Now, if you don't have 366 pencils at home, you can do the same thing with toothpicks.
Now, if you want to research this on your own to find the instructions, just try looking up pencil cube. Okay, that's not the only thing we can build with pencils. Check this out, a pencil asterisk. Phil, can you max it out and add some more pencils? Yeah, so I did. I maxed it out with even more pencils. And then I thought, well, could I max it out again? So I did. This is what it looks like with even more pencils. And in fact, I removed the inside pencils and the whole thing still stays together. And then, of course, this is the maximum number of pencils you can do with this configuration, because as you can see, it starts to become a sphere and you kind of run out of pencil length. There you go, maxed out pencil structures. Of course, I've used all of my pencils, but that's okay, I will buy some more. I will just write myself a note to buy more. Actually, there are sharpened pencils on the bottom of my pencil cube, so I'll just write this note with the pencil cube. What could possibly go wrong? Okay, ready? 1, 2, 3. And it's still standing! Oh, that one's not sharpened. Oh, here we go. Where'd my book go?
Ooh, look at Sarah and I have maxed out a geodesic dome out of gumdrops, oranges, watermelons, and more gumdrops. But now we're making one using glue and cardboard circles.
Are those the same distance?
After a bunch of time assembling and gluing, we have a giant maxed out dome.
Okay, there. Are we done?
I think so.
We're done!
Yeah.
Yeah! Max out dome. How many points do we have?
So many.
Do you think we can lift it?
I think
I think
so,
that's the
yeah.
top. Try it.
See.
Okay, whoa. Whoa! Wait, we can spin it!
It was really light and also really strong. Strong enough to hold upside down.
As a fruit bowl, it'd be pretty good. This is so strong. I'm surprised at how
strong this structure is.
There you go, Science Max, experiments at large, geodesic dome. And now it's sort of a geodesic disco ball. I like it. Whoa, 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 okay, careful. Careful, careful. All right, putting it down, putting it down. Oh, greetings, Science Maximites. My name is Phil, and I think I might have overdone it with the science. I mean, what's a better use of science than creating a whole bunch of slime? Well, I did, and you know what? It's really cool. Slime. I love slime. It always makes me feel like a mad scientist, but I need a good mad scientist laugh. Yeah, it needs work. Anyway, today we're talking about polymers. Polymers like slime. But you see, polymers aren't really a substance. They're more how something is constructed. And there's all kinds of different polymers. There's slime, obviously, and rubber polymers like, well, like rubber. And there's also hard polymers like plastic. Now, polymers are all kind of constructed the same way. Like this. This is a chain. Yeah, so imagine this is a chain of molecules, and all the molecules are the same, and they just repeat in a long line. Now, when you get a polymer like slime, all the chains are not connected or very loosely connected, which means that they can flow over each other like a slime or sort of like a liquid, and they behave like that. So that is slime. But when you get to a rubber polymer, you start to get little bonds in between the chains of polymers that work like this. You see, they still move around a little bit, but they can spread apart, and they become flexible and bouncy. Yeah, I know, a chain doesn't really bounce, but rubber polymers do. Huh? Now, when it gets to a solid polymer like plastic, there's a lot more links, and it's all kind of interconnected, and it doesn't move at all. It doesn't move. Okay, again, harder to tell with a chain, but plastic is very hard and rigid. So let's dive into the world of polymers and make some slime. Yeah, too mad, not enough scientist. I'll keep working on it. Anyway, to make slime, take your white glue and pour in an amount. It really kind of depends on how much slime you want to make. Now, you want to add about twice as much water as that. Yeah, we're somewhere around there. Great. Now we want to put in just a little bit of soap. Maybe there, that's good. And you want to put in your food coloring. I like green. Green seems like the right slime color to me. It's the right appropriate mad scientist kind of slime. And then you want to start mixing that up till you get the right kind of consistency. That means make sure the glue and the water are equally mixed up. Good. And now we're ready to make it an actual slime by bonding the polymers together by adding liquid starch. Very good. And you want to mix it up.
When you add the liquid starch, it starts to bond the chains of molecules together, changing it from a liquid to a slime.
It's coming along. And there you go, slime. Now, if you want clear slime and not opaque slime, you want to use clear glue and not white glue. But that's basically the recipe. So there you go, slime. Too supervillain? Yeah, okay, well, anyway, all right. Now all you need is an expert to help me max it out. Of course, my interface is hand gesture based, so I don't know if the slime. Oh, hey, there we go. Great. So you get it. Oh, of course. Sarah from Mad Science. Mad Science, they really know their slime. This is great. Okay, I got it. Close. There we go. All right. Ugh. I'm not sure if bringing it through the portal is such a good idea, but at least I'll have it on the other side. Ugh. I have a pot. Why do I have a pot? I didn't have a pot when I went through the portal. Is someone somewhere missing a pot, or did it just create this pot out of nothing? Huh. Hey, Sarah!
Hi, how are you doing?
Good, Sarah from Mad Science, you're gonna help me make some slime.
Yes, I actually brought some. Oh, this isn't slime, this is a pot lid.
Hey.
Oh,
Well, at least we have a set. Doesn't answer any questions, though. And I guess we're gonna have to make some more slime.
definitely. What kind of slime do you want to make?
What do you mean, what kind? Is there more than one kind?
Oh yeah, there are tons of different kinds of slime with lots of different ingredients and recipes.
Oh, I only know the one. Can you show me all the others?
Of course, let's go make some right now.
Okay, great.
Awesome.
Come on down to Sal's Science Shop and see me, Sal, while you shop for science.
This week only, Sal's one-of-a-kind, once-a-year polymer sale.
50 to 75% off anything made of polymers.
Rubber? That's a polymer. Polystyrene.
When you're eating your next meal, I recommend some polypropylene.
Low-density polyethylene.
High-density polyethylene.
You want some polytetrafluoroethylene? We got it.
We've even got polychlorotrifluoroethylene.
Do they even know how good a deal this is? Because you're not gonna find that kind of deal just like every day.
But hold the phone. Polymers aren't just plastics. Rayon, nylon, Teflon, you name the lawn, we got it on sale.
What do we want?
Polymers.
When do we want them?
Anytime during normal business hours.
Wool,
Silk, even cotton. Polymers, polymers, polymers. Polymers, polymers, polymers. Word has lost all meaning.
glue, paint, umbrella fabric. Oh yeah.
Carpet?
You bet that's on sale.
Roberta, I'm running out of sale signs. Buy it and I'll put it in a plastic bag, also made of polymers. Seriously, Roberta, we can't have a sale on everything. Oh, hey, even you, even me, the proteins in our bodies, even our DNA, all polymers. So come on down to Sal's Science Shop and get a great deal on your polymers for a limited time. I mean, it'd have to be a limited time, right, Roberta? Because, I mean, I can't discount everything in the store to 75% off. How am I gonna make any money? I mean, are we still rolling?
100 different kinds of slime.
Yes, it's gonna be so much fun, but we're not gonna make 100 today.
Yeah, I know. We're just gonna do our top favorites.
Yeah, it's gonna be super great.
All right, what are we starting with?
So our first slime we're starting with today is some really cool molding slime. Now this slime, actually, if you leave it out overnight, it'll harden and you can make an imprint of whatever you like. So here, we made an imprint of our little tool there. So we're gonna look at a little bit more liquidy slime, starting with this one over here, which I believe you already know about.
This is cornstarch mud.
Exactly.
You hold this.
Sounds
I'm gonna
good.
hold this and we're gonna try pouring it. Whoa, oh,
Whoa.
so, see, it's like a liquid, but then if you do it fast, it's like a solid. All right, what's next?
Over here, we have some other really awesome types of slime. So right over here, we have some crunchy slime.
Crunchy slime?
Exactly.
Why is it crunchy?
Now it's crunchy because we've actually added a few beads inside of it to make it crunchy. So this is some really cool, awesome slime.
Here, you take half.
And you can feel the beads as you get to stretch it out. It's so cool.
This one is a little harder to clean.
Exactly.
I'll just do that. All right, so what's next?
So next we have some really cool glow-in-the-dark slime.
Glow-in-the-dark slime?
Yeah, it's so awesome.
Ooh, look at how much it glows. That glows a lot. That's super glowy slime. So to do the different kinds of slime, we need the polymer.
Yes.
And then the thing that sticks the polymers together.
Exactly.
So the glue is the polymer.
Glue is the polymer.
And the starch is the thing that bonds it.
Yes.
Uh-huh.
Very cool.
And then you put the thing in that makes it the kind of slime.
Yes, right before you add the bonding component, because if we keep adding stuff after it's already made, it unfortunately won't be able to take it. So we add our powder before we add our starch in this situation.
Should we go on to the next thing?
Yeah, let's move on to
More slime! Plastic is great and plastic is everywhere. But the problem with plastic is it isn't very biodegradable. It doesn't break down in the environment. I'm still on hold. Oh well, there you go. Back for another couple years, I guess. But here's a way that you can make bioplastic. It's fully biodegradable because it's made of natural materials.
The recipe is easy. 2 parts cornstarch, 3 parts water, a few drops of cooking oil, and some food coloring to make it whatever color you want.
Purple, science purple.
Mix it up and it turns into a paste.
Now what you'll need are 2 things. 1, an adult, and 2, a microwave.
Put it in for 30 seconds.
Clock wipe. There we go.
Then take it out and mix it some more until it cools down. Then you can pull it out and use your hands to sculpt it into a shape or take the shape of something else.
Once you put it all the way around, you can turn it into a little flower pot.
Once you've sculpted it,
You need to wait for it to dry, which will take about a day. Clock wipe.
after waiting a day,
Huh? What? It's been a day? Oh.
you have something made out of bioplastic. Like this little flower pot you can use to grow a small plant.
And then when it grows big enough, you can take this biodegradable flower pot and plant it right outside in the dirt, and this pot will biodegrade and turn back into dirt. Pretty cool, right? Well, let's max it out. Biodegradable frisbee. Check it out. It's a frisbee, but it's biodegradable. So you throw it around in the park, but if you lose it, it turns back into dirt. Ha-ha! What, not enough? Okay, clock wipe. Biodegradable lawn chair. Use it for one season and then return it to the earth afterwards. I think this is one of my best Science Max. Okay, bioplastic lawn chair, not as strong as regular lawn chair. We've learned that lesson now, so that's good to know. I mean, how would I have known if I hadn't tried it?
Sarah and I are looking at different recipes for slime.
All right, what do we got here?
So over here we have some amazing foamy slime, which has so many ingredients in it. Here, watch what happens when we start pulling it out.
Ooh, wow. So it's like,
Super stretchy and super fluffy.
here, that's great. Okay, now you gotta hold yours. You gotta hold this end. Okay, you take, and then take some more. And then we take that. And then, yeah. It gets thinner and thinner, and it becomes more and more lines of foamy slime.
Yeah. And the last kind of slime we made today is some classic flubber slime.
Ooh.
So much fun.
Now, why do you think it's called, is it flubber slime? Because is it really a slime?
It is a slime, yeah. It's super fun and it's super stretchy.
Oh, okay, I get it. Look at that, and it's sort of like a little bit like gelatin.
It is almost like gelatin.
Here, you can have some. There you go. Whoa. Ah, whoa. All right, so Sarah, now what we need to decide is how we're gonna max it out.
Right.
Like, should we just get a lot of slime?
That sounds like a really good idea, but we are gonna need something to put it in because we can't just have slime all over the floor.
Okay, you're right. So we'll get some sort of container thing.
Yeah.
And we'll see how much slime we can make, and then we'll just play with it and see what happens.
Sounds good.
And yeah, we will experiment because it's science.
Yeah.
Okay, high five. Careful high five so we don't splatter. Okay, good. Okay, let's go. This is right.
This is a rubber glove. Well, actually, it's a latex glove. What's the difference? I will get to that in a second, but I'm sure you can agree it's super stretchy. How stretchy? Let's fill a rubber glove with water and see how big it gets. So, difference between latex and rubber. Well, it all comes from a rubber tree. Well, actually, it's a fake tree. It's just to show you how it works. The sap of the rubber tree is collected just like this. There's a spigot, and then the sap goes out, and it's collected. It's the same way that the sap for maple syrup is collected. And this is natural latex. If it's dried out, it becomes natural rubber. Latex generally means the liquid form, and rubber means the solid form. But wait, then why is this a latex glove? The glove is not liquid. What's the deal? Well, generally, latex means water-based or liquid, like latex paint. But it could also mean synthetic latex. That's latex that's man-made and doesn't come from a rubber tree. So, we call rubber gloves because they used to come from rubber trees, but now they're usually made out of man-made latex. But either way, they're super stretchy. I wonder how big this is gonna get. Science! Sarah and I are maxing out polymer slime. How? Maxed out tub of slime! Whoa! Okay, so how do you feel? Are we mixed up enough? First, we mix up a bunch of slime in a garbage bin. So with the polymer chemistry,
the polymer is generally a liquid, right?
Yep.
And the bonding agent makes it stick together. So the more we use, the more of a solid we get.
Exactly, yeah.
So we want to split it and make it sort of halfway between a liquid and a solid, and I think we're exactly at the right stage.
It looks perfect.
Oh, yeah. Okay, so let's dump this garbage can in.
All right.
All right. Then we dump it in.
Oh, gross.
Turns out we needed more slime.
I don't think that's gonna be enough.
I think we may need some more slime.
Yeah, how much more do you think we need?
So we added 11 more.
Ah, delicious.
Perfect.
Last one. Oh, yeah. Then we experimented.
Oh, yeah. We have a giant tub of slime.
Because the slime is stretchy, it created amazing bubbles.
So do you think I could blow a bubble with the slime?
Well, maybe not you, but definitely
wanna
the air
try this?
compressor.
No, no, I'd have to just put it on my face. I think I've already got it on my face.
Then there was only one thing left to do.
We get in the slime.
Can we do that?
We can totally do that. This is science math.
That's so exciting!
Going swimming in slime.
Yes!
Who's going first?
You are!
I am, obviously. All right, this is how Science Max does polymers. 3, 2, 1.
Plastic is everywhere, but what can we do with it aside from recycle it? Well, we can reuse it to make cool plastic charms. But you're gonna need the right kind of plastic, and you need polystyrene. Just look for the little number 6 inside the recycle symbol.
Cut out some plastic and decorate it however you want.
There we go. Haha, check it out. The Science Max logo. Also, I've made a couple other things. I've got a chemical symbol, an atom, and this is me in some slime.
Then get an adult to help you put it in the oven or
Toaster oven.
at 350 degrees. It only takes a few seconds for the plastic to shrink to 1/3 its size.
The reason why this happens is when plastic is manufactured, it's heated and stretched out and then cooled, and it sort of freezes in that stretched out shape. And when you reheat it, it shrinks back down to the unstretched shape.
Get your adult to take it out and wait for it to cool, and you'll have yourself some small plastic designs you can use for keychains, bracelets, name tags, bookmarks, whatever you want, all using the power of polymers.
Awesome, I'm gonna make all of those. What was that again? Keychain, ornament, magnet.
Magnetic putty in 60 seconds.
This is magnetic putty.
Thank you.
This is magnetic putty.
10 take.
This is magnetic putty.
26.
This is magnetic putty.
2,635.
This is magnetic putty.
I can't count this high.
This is magnetic putty. Magnetic.
Oh, it's not a magnet, it's attracted to magnets. Oh, that makes more sense. This is magnetic putty, and this is a magnet. The putty is made of polymers, which means it can flow over itself. It also has lots of iron filings in it, which is why it's attracted to magnets.
This is what happens over several minutes.
And there you go, magnetic putty.
Okay, so where were we? Oh, yeah.
3, 2, 1. Yeah!
And remember, don't try this at home.
Slime!
Sarah and I enjoyed our maxed out tub of slime. So let's recap. Slime is made of polymers. Polymers come in a lot of different forms. It's all about long chains of molecules. And none are more fun to swim in than slime.
Do I have slime here?
Yeah, definitely.
Slime here! Slime!
Max experiments at large. Polymers. Slime. Yeah. High fives. Yeah. Slimy high five. Yeah.